Okay, guys, today we're going to talk about phases. So the phases of matter. Please have your Chapter 9 guided notes out and be following along and filling in the information as we go through these slides. And hopefully we'll learn something. So let's get started. There's three main phases of matter. Okay, three main phases. So let's list them first. So there's a gas phase, there's a liquid phase, and there's a solid phase. So solid, liquid, gas. We've heard about these phases of matter, ever since you've been in probably first grade. Now we're going to talk about them in a little more detail with the chemistry that we've learned already. So the strength of the intermolecular forces determine what phase the substance is in. For example, if there's weak intermolecular forces, so if the intermolecular forces are pretty weak, what's the weakest intermolecular force we just talked about last time? Dispersion forces. So the weakest ones are dispersion. If it's weak, you can see that the substance is in the gas phase. If the intermolecular forces are somewhat medium in strength, you might see that the substance is in the liquid phase. And then you can probably guess the solid phase has the strongest intermolecular forces. So solid. So before we start, I wanted to get an idea and visualize the three phases of matter. So I would like you guys to do this on your book somewhere. On the top of that page probably. That would be a good spot. Let's write the gas phase. Draw a box for the liquid phase. And draw a box for the solid phase. Now let's get an idea about how the molecules are arranged. So in the gas phase, there's a lot of molecules and they're spread out, kind of just placed randomly. And these molecules are just buzzing around at high speeds in the gas phase. In the liquid phase, now they're somewhat closer together, and they're kind of organized. But these molecules are allowed to kind of slide past their neighbors. So they're moving and sliding past their neighbor. Okay, now let's go to the solid phase. The molecules in the solid phase are very close together, and they're just sitting there, vibrating in place. Okay, so I think we kind of get the picture there. In solid, these molecules are very close together, just vibrating in place. I want you to keep that in your mind as we talk about these phases today. Think about how the molecules are arranged in each phase. So let's look at the gas phase first and talk about it in more detail. So gases consist of small particles that are separated from one another by empty space. So the distance between these molecules is there's a lot of distance, and they're just separated by empty space. And they're moving around in kind of random motion all over the place. The intermolecular strength is weak. The gas particles are moving in fast, constant, random motion. So the air molecules in this room, they're moving around, pretty fast. At a constant motion, they're just going in random directions. They bounce off each other, and that's what's happening in the gas phase. Now here's a common theme we're going to see today. If you took a gas and say you increase the temperature, so as the temperature increases, what's going to happen to the gas particles? Are they going to speed up or slow down? Yeah, when you heat them up, particles move faster. As the temperature decreases, so if it got colder, so if the temperature was to decrease, the gas particles would slow down. So on a really hot day, the air molecules are moving faster. On a cold day, they're moving slower. Now this animation here is supposed to be a magnifying glass. And I know you can't see atoms, but let's just pretend that you could. What would they look like in the gas phase? And so these molecules or these atoms here are spaced apart. There's a lot of space between them. And they're moving very quickly in just kind of random motion here. So that's what it would look like if you could see air molecules moving around. Okay, liquids. Let's go to the liquid phase now. Liquids are made up of particles that are somewhat close together. So they're closer than they are in the gas phase. So they're somewhat close together. And the particles in the liquid can slide past each other, so they can kind of move by each other. The intermolecular strength in the liquid phase is medium. The stronger the intermolecular strength, the more thick or viscous the liquid will be. So viscosity is kind of this measure of how thick that liquid is. Well, if you have stronger intermolecular forces, it becomes more viscous. If they're somewhat weaker, then it's going to be more, I guess, runny. It will run faster. Actually, motor oil, they measure motor oil by its viscosity. And so you can get really thick motor oil or very more runny motor oil. And so that is all determined by the intermolecular strength of the molecules in that particular substance. Okay, and again, if we increase the temperature of a liquid, what's going to happen to the speed of the particles? Well, they move faster. The speed is increased, making them move farther apart. So these molecules move faster, which moves them farther apart. And this extra space between the molecules weakens the intermolecular forces. So the farther they move apart, the weaker those intermolecular forces become. So maybe we should talk about this. If you had a pot on the stove of water, and so this is on a stove here, you're heating up that water, right? What's going to happen to the speed of the water molecules in this pot? Yeah, they're going to start moving faster. And they're going to slide past their neighbor, and it's going to move faster and faster. And the distance between those molecules is going to what? Increase. And so these water molecules are getting farther apart, and that weakens the intermolecular forces. Will you reach a point at which you're heating this water up, and they're moving so far apart in the liquid phase that one of these water molecules could fly off and become part of the gas phase? Yeah, and we've seen this. When you boil water, that's what's happening. You're giving it so much energy that these water molecules are moving fast enough. At boiling point is when water can actually escape the liquid phase because they're moving so fast and become part of the gas phase. So that's what they're saying. Okay, if you could look at the molecules in the liquid phase, here's what they would be doing. Okay, they're somewhat close together, but they're able to kind of slide past each other, slide past their neighbors. So that's what they would be doing. All right, let's talk about some characteristics of the liquid phase. One thing that we should learn about is surface tension. Surface tension is the force holding the surface of the liquid together. So it's the force holding the surface of the liquid together. So it's the surface, whether it is a pond, whether it's a little puddle, whether it's an ocean. Surface tension happens at the surface and it holds water together. That force that's holding water together is called hydrogen bonds. That force of attraction between water molecules pulls the water molecules together and they kind of hold on to each other like magnets. Well, the stronger the attraction between the particles, the stronger the surface tension. So this is water down here, and that's because of the hydrogen bonding in water. You have some surface tension which allows this little guy to walk across the water. So if you don't have very much weight, the surface tension can be stronger and holds you on top of that water. It's also what is responsible for water droplets. The water sticks together because of hydrogen bonds. It's cohesive. So water sticking to water, and it makes a water into this little droplet. Instead of spreading out flat on the leaf, water likes to stick together, and so that's why you see it as water droplets. Another property of water that we should study is cohesion and adhesion. So first of all, cohesion. It's a force of attraction between identical molecules. So this could be between water and another water molecule. So cohesion, it's caused because of hydrogen bonds. So when water is attracted to itself. Let's contrast that to this one, adhesion. Adhesion is a force of attraction between molecules that are different. So an example of adhesion would be water being attracted to glass. Those are different substances. An example of cohesion and adhesion is seen in capillary action. Capillary action is a very important scientific principle, and it's easy to demonstrate. You could get a dish of water here and put some food coloring in it. And if you got glass tubes of varying diameters here, so this one's very small diameter, medium, and they're getting larger. What you will see if you put these glass tubes in the dish is that the water, without helping it, the water will climb the tube. It seems to defy gravity. Why would it do that? Yeah, because water is adhering to the glass, these glass on the sides here. It adheres to it, and it kind of pulls itself up, and it stays together because water is cohesive. Water likes to stick to itself, so these water molecules, because of hydrogen bonding, stick to each other, and it just pulls itself up. Now, what do you notice about the height that they will get to when you compare that to the diameter of the tubing? Good. If you have a smaller diameter tube, this water will climb even higher. The larger the diameter of the tubing, it doesn't climb as high. And this picture over here is trying to show you the difference between cohesion. Remember, cohesion is between molecules that are the same. So cohesion happens between water molecules. Adhesion is when they're different, so water being attracted to glass. So the adhesion is just seen right here, and this water molecule being attracted to this glass, and cohesion is between water molecules. So one of the applications of this is water transport in trees. Have you ever wondered, this is a big sequoia tree, very tall. Have you ever wondered, how does water get to the top? Because this part of the tree up here needs water too. Well, where does water enter trees at?
Or at the roots.
At the roots. So clear down at the base of this forest here on the ground is where this tree is absorbing water. How does it get to the top of the tree?
Through the middle of the tree, through the...
It doesn't even have a pump. Like we have a pump in our body to get blood up to our head and everywhere that we need it. Trees don't have pumps. How does it work? Good. Capillary action, adhesion, and cohesion. This is happening in plants as well. So you see here on this slide, capillary action. So the water's being absorbed in the roots. It goes up these tiny vessels in the tree. Do you guys remember from biology the xylem and the phloem? These little vessels that go through the tree. Well, the xylem carries water up. They're very small tubes. And because water, hydrogen bonds between water molecules. So this hydrogen bonding here, as it pulls the water up, the hydrogen bond keeps these water molecules together. And so you can kind of think of it as beads on a string. And so here's a water molecule, hydrogen bond. Another water molecule, hydrogen bond. Another water molecule. And it just keeps going up to the top of the tree or the plant, whatever it is, until it leaves the leaf. It's evaporated from the leaf where transpiration takes place. And it's just pulling it like beads on a string. And that's how, even at the top of a redwood or a sequoia tree, water can get to the very top. And it takes a lot of water for that tree to live. It's kind of amazing that that happens. So that's one of the cool applications of cohesion and adhesion. Okay, before I move on, let me see if you got that. Cohesion is water being attracted to who? To water. Adhesion is water being attracted to something else. Yeah, whether it's glass, whether it's the sides of a xylem vessel, it's just something else. So, okay, very good. Now one more phase to look at, the solid phase. Solids are made up of particles that are very close together. The particles in a solid, they still move, but they're so close together that they're able just to vibrate in place. Okay? So they're just vibrating in place. So even the atoms that make up this counter here, the atoms, if you could look at them in some powerful microscope and see them in real time, they are moving. They're just vibrating in place. So all atoms, all molecules move. Okay, the intermolecular strength is very strong in the solid phase. It's what holds them very close together. And same trend here with temperature. If you increase the temperature, what happens to the speed of the particles? Well, they increase in speed. If they increase in speed, this weakens the intermolecular forces between them because now they're moving faster and farther apart. Can you go from the solid phase to the liquid phase if you got it hot enough?
Yeah.
Sure. What do we call that? Melting. Yeah. So what that's talking about here is melting. When you melt something, they get the temperature so hot, these molecules move faster and faster, and they get farther apart, which weakens the intermolecular forces, and it can actually go into the liquid phase. Good. All right, if you could see what the particles are doing in the solid phase, they're very close together and they just sit there and vibrate in place. Just vibrating in place. Okay, I think this is a good time to talk about this. I kind of like to visualize things a lot, and anytime you can visualize it, I think it's better in chemistry because we can't see what the molecules are doing. So this might work, it might not. Let's try it. So even if you're watching the video, so I want you to make fists. Okay, you got two hands, so make two fists. And I'm going to go through and show you. We're going to pretend that these fists are your molecules, and you're going to show me what the molecules are doing in each phase, solid, liquid, and gas. Let's start, since we're talking about solids right now, let's start in the solid phase. Okay, so they're very close together. So put your fists very close together, and they what are they doing? They're just vibrating in place. So you just vibrate. So just move both of them back and forth. Okay, and that's what they're doing in the solid phase. Okay, now show me what they would be doing in the liquid phase. So in the liquid phase, they move a little bit farther apart. They're still pretty close together, and they just slide past their neighbors. So you're just moving them past. Your fists are just moving past each other. Okay, that's the liquid phase. Now show me what they would be doing in the gas phase. In the gas phase, there's a lot of space between them. They're just flying in random directions. So you're just kind of waving your fist around in the air, right? Okay. Hey, don't be too cool to be a gas. Come on. Show me what a gas phase is doing. Now, let's say you go to the liquid phase again. Go to the liquid phase. Okay, the fists are sliding past each other. Now go to the solid phase. Okay. I want you to keep that in mind as we talk about the rest of this lesson today. Okay. So in the solid phase, like it shows here, very close together, just vibrating in place. Liquid phase, and then the gas phase. They're very far apart, moving a lot faster. All right, to finish up the introduction to phases, I've got this phase summary table in the guided notes. So I'd like you to fill this out. Guys, everything on this table is very important for you to know. So as you're writing it down, pay attention and try to learn this stuff. If you're watching the video, please hit pause and fill out your table before you move on. Okay, so hopefully you got this table filled out. I just wanted to go over it real briefly. In the gas phase, the distance between the particles is large. Liquid phase, they're closer together, so it's somewhat medium. In the solid phase, the particles are very close together, so the distance is very small. The particles are flying around in the gas phase. They're sliding past each other in the liquid phase, and they're just vibrating in place in the solid phase. Intermolecular forces, if they're very far apart in the gas phase, it makes sense that these forces holding them together are very weak. Medium in the liquid, and since in the solid phase they're very close, it makes sense that they're a lot stronger in the solid phase. Now temperature. This is an easy trend to remember. If you heat something up, the particles move faster. What's the opposite of that? If you cool them down, they're going to go slower. Okay. All right. for the second part of this lesson, we're going to talk about phase changes. Phase changes. Phase changes occur because of substance gaining or losing heat.
I've got a question.
Phase changes occur because they're gaining or losing. Okay, so we're really going to pay attention to what's happening with heat, guys. So just to help you remember what heat is, I've got a couple of things to talk about. Heat is the transfer of energy from an object at a higher temperature to an object at a lower temperature. So a couple things I want you to remember. Heat is energy. So it's a transfer of energy. It's a flow of energy from high temperature to what? To lower temperature. So when you touch, like say it's cold outside and you touch the door handle, doorknob. How come it's cold? Explain it to me. Why is it cold? Is it cold because the cold from that doorknob is coming into your hand? Or is it cold because you're losing heat to the doorknob? Yeah, that's what we mean when we say cold. We're losing heat. So when you touch something that's at a lower temperature, because your hand is now at a higher temperature, it's going to lose heat. So heat is going from your hand to the doorknob. That losing of heat is what feels cold to us. Okay, so it's a little bit different in how you think about that. There's a law of conservation of energy, very important, which says that you cannot create or destroy energy, but it can change forms. So heat is a part of energy. You can't destroy it. Heat is going to flow from one object to another object. The energy can't be destroyed. And so we're going to study heat flow with these phase changes. And I want you to be able to describe which direction the heat is going, whether it's flowing into the object or into the surroundings. Okay. So I think you had to write the law of conservation of energy, right? Okay. We're going to talk about it in terms of heat. Heat is energy. So okay, let's get started with phase changes. On your book, on your notes, I think I've got a picture that looks a little different than this. I think for the gas phase I drew where there's a cloud. Okay? But I want you to write, inside that cloud, I want you to write gas. Okay? For solid, I have, I think, a cube. So inside that cube, write solid. And then for the liquid phase over here, on your notes, I think I have just a puddle of water there. So inside that puddle, write liquid.
On ours, it says you can't go from a gas to a solid.
Good. Yeah, that's another point that's different. From the cloud to the solid, I want you to draw in another arrow that goes from the cloud to the solid. So you're going to have to draw in this arrow.
Why doesn't ours have that?
I don't know. I should add that in there. But if you guys will help me out and just draw it in right now, that would help me. Okay? Because we're going to put something in those arrows. Let's go through these phase changes and what they're called. Okay, let's start with the easiest one, maybe the one that you're most familiar with. Let's go from a solid to a liquid. What do we call that phase change? A solid to a liquid. Melting. So in that arrow that goes from the cube to the puddle, you're putting melting. That's what we call it. It's called melting. Now let's go the opposite direction. Now let's go from the puddle back to the cube, the ice cube. So what do we call that? Freezing. Okay, so in those arrows, I hope you're writing these phase changes. Okay, now let's come back over here to this puddle, to the liquid, and let's go up to the gas phase. What do we call that? Vaporization. Yeah, so in that arrow that goes from the puddle to the gas, the cloud, you're writing vaporization. Now let's go from a gas to the puddle, to the liquid phase. What phase change is it called when we go from a gas to a liquid?
Condensation.
Condensation. Yep, that's what it's called.
Wouldn't vaporization also be evaporation?
Good, yeah. A lot of people think that you can just put evaporation. We'll explain the difference between vaporization and evaporation in a second. Good question, though. So hold on. I promise I'll answer that question in a second. Okay, now let's go to the one where people we're not really that familiar with. Let's go from this solid state, solid phase, to the gas phase. What do we call it? Solid to gas. Sublimation. Yeah, when something sublimes, it's going from the solid phase to the gas phase. Now, most substances don't do that. Most substances will go from a solid to a liquid, then to a gas. But there are some things that go directly to the gas phase. And I promise I'll answer that question, what substance does that, in just a second. Okay, now let's turn around. This is the one where you had to draw in the arrow. But going from the cloud, the gas phase, to the solid, what do we call it? Deposition. Deposition. Okay, so how many phase changes are there?
6.
There's 6 of them, and you're going to have to know all of them. Okay? So let's go through them in more detail. And I want to talk about a couple of things. One, what's happening to the distance between the molecules as you go through that phase change? What's happening to the strength of the intermolecular forces? And what's happening to heat flow? So you're going to have to be able to describe all those changes with each one of these phase changes. Let me show you what I mean. So melting, let's talk about that first. Melting, you're supposed to write this down, is going from a solid to a liquid. So we've got a solid material here. The particles are very close together. And we're going to a liquid where the particles are a little farther apart. Okay? So let's answer these questions. The distance between the molecules gets what, guys? Gets larger. Yeah, when you melt something, the distance between the particles gets larger. There's more distance between them. Okay? What do you think is happening with the strength of the intermolecular forces?
It's smaller.
Yeah, they're going to get weaker. The intermolecular forces will become weaker because they're moving farther away. So there's weaker forces because there's more distance between the particles here. Does that make sense? Okay, now let's talk about it in terms of heat flow. If you have a piece of ice here and you want to melt it into this puddle of water, does heat have to flow into the ice cube or out of the ice cube?
Out. Go around it, has to like hit it and break down the molecules of it goes.
But doesn't that... How do you melt ice, guys? You have to, you have to put it in a warm environment, right? What's happening there is heat has got to flow into it, right? Doesn't heat have to come in and then it will melt it into this puddle?
Yeah.
Okay, so heat's got to flow into.
How does it automatically go through the heat? Okay, never mind that.
Okay, so melting occurs when heat flows into the solid object. It's got to flow into it. So remember, heat always goes from hot to cold. So when heat flows into it, you can melt it. All right, the melting point, that's what it's called. This temperature at which this happens is called melting point. What is it for water, guys? What's the melting point of water?
32.
Yeah, anything that's above
32 degrees.
32 degrees Fahrenheit. What is it if we did Celsius? Because we're in science class, we should really do Celsius. 0. So anything above 0 degrees Celsius, water is going to melt. Now this melting point is different for each substance. So if we're not talking about water, we can't go with these numbers. That melting point is going to be different. Okay. All right, let's talk about freezing. Freezing is when you go from a liquid to a solid. So we've got this puddle, and we want to freeze it into a solid. Before I put the answer up, guys, what do you think is happening with the distance between the molecules? It gets closer together. So the distance between the molecules gets smaller. Yeah, the distance between the molecules gets smaller. They get closer together. Before I put it up, what do you think is happening with the strength of the intermolecular forces here?
Stronger.
They get stronger because they're getting closer together. Those forces get stronger. Now, let's talk about the heat flow. Does heat have to flow into this puddle to make ice, or does it have to flow out? Does this water have to gain heat or lose heat?
Lose heat.
It's got to lose heat, so heat flow has got to be out. When the water loses heat in the liquid phase, it's going to become solid water or ice. So heat flows from water to the surroundings, and the particles lose energy and they freeze. Okay, this point at which this happens is called the freezing point. Again, it's different for every substance, but what is it for water? 32 degrees Fahrenheit or 0 degrees Celsius is when it will freeze. Okay.
How can it freeze and melt at the same temperature?
Well, that's why I said melting has to be above,
Oh.
greater than, and freezing will occur at 0 degrees Celsius or 32 degrees Fahrenheit. Good question. Okay, vaporization. This is a good one. Vaporization, what are we doing here? We're going from a liquid to a gas. So now we've got this puddle of water, and we want to make it into the gas phase, so we're going to make some steam here, like that. Before I put it up, what's happening to the distance between the molecules when you vaporize it? The distance gets larger, right? So the distance between the molecules gets larger. What's happening to this intermolecular forces?
It's weaker.
They get weaker because you're spreading them out more. There's more distance here. The intermolecular forces become weaker. Now, heat. Let's talk about heat flow. For this to happen, does heat have to flow into the water in the liquid phase or out of the water in the liquid phase?
Into the water.
Yeah, heat has got to flow in. It's going to speed up the molecules in the liquid phase so much that they will actually escape the liquid phase and fly off into the gas phase. Okay, so heat is absorbed by the liquid from the surroundings. Now, Kale, going back to your question about evaporation. So let's learn the difference between evaporation and vaporization. Evaporation is vaporization only at the surface. Only at the surface of a liquid. So if you're looking at a lake in the summertime and it's really hot, you can see the water almost is going to evaporate just from the surface. It's not happening from the bottom of the lake, is it? It's just happening from the surface. So when you see vaporization at the surface, we call it evaporation. Okay, this is called the boiling point. Okay? The temperature at which the vapor pressure of a liquid equals the atmospheric pressure. Now, people think all the time in order for this to happen, you've got to be to a really high temperature. But did you know we can boil water at room temperature?
Yeah.
How do you do that?
You remove the air pressure.
Yeah, you decrease the air pressure around that water, and then the vapor pressure equals the pressure around it. It's gonna boil off.
Is it still hot?
Okay, and it's not hot.
It's not hot?
No.
You can put your hand in like boiling water and it's not hot? That's cool.
Yeah, it wouldn't be hot. It's just so there's more to go that goes to phase changes than just temperature. Also, pressure goes into it, and temperature and intermolecular forces have some effect as well.
That's cool. You should try it.
Okay, I can show you that. Yeah, we should do that. Condensation. Keep going. Condensation is when you go from a gas to a liquid. So now we've got this gas phase here, and we go to a puddle. If we're talking about water. before I put up the answer, what's happening to the distance between the molecules here? Yeah, they're gonna get closer together. So the distance between molecules gets smaller. And what do you think is happening to the strength of the intermolecular forces? They get stronger. Yeah, they get closer together. They got to get stronger. So, good job. So the intermolecular forces get stronger. All right, heat flow. Let's talk about that. Do you think heat's got to flow into this gas, or do you think it's got to lose heat? Yeah, it's got to lose heat so that these particles slow down, and they can get stronger intermolecular forces. They're closer together. It becomes a liquid. So heat flows out of the gas. Heat flows from the water vapor to the surroundings. All right, now condensation, we're very familiar with this. Whenever you get a cup of ice water and you leave it out, especially if it's a very warm day and you leave it outside, you see these little droplets of water on your cup, right? We've all seen that. Where's that water coming from? Is it somehow going from the inside of the cup to the outside? No, not at all. Where's it coming from? From the water in the air that's in the gas phase here. Now, if it's in the gas phase here and it hits something really cold, what happens to the speed of these gas particles? They slow down. And when they slow down, they get closer together. There's a point at which they get so close together that it actually forms the liquid phase of water. And you'll see little water droplets here. And so that's where it's coming from. It's coming from the air. And you might have noticed this if you take a shower, a really hot shower, and you see this on your mirror. Again, when the water in the air in the bathroom hits the colder mirror, it condenses it into water in the liquid phase. Okay, very good. Let's go to sublimation now. This is one we're not so familiar with, so it's kind of cool to talk about. This is going from a solid directly to a gas. Okay? So we've got a solid here, and most things go from a solid to a liquid to a gas, but there are some things that go directly from a solid to a gas. So before I show you, you predict what's happening to the distance between the molecules here. Good. Yeah, they're getting a lot farther apart, right? So the distance between the molecules gets larger. The distance between the molecules gets larger. What's happening to the strength of the intermolecular forces? They're getting weaker, a lot weaker. Yeah, because they're moving farther apart, so these intermolecular forces become weaker. Let's talk about heat flow for a second. If I have a solid here, does heat got to flow into it or out of it in order to make a gas? Yeah, heat is going to be flowing in because you got to speed up these particles in here. Speeds them up, it makes them go faster, and the distance between them gets so large it can actually go to a gas. Okay, so what substance does this that we have experience with? Dry ice. Okay, so if you look at dry ice, here's a piece of dry ice. What's coming off of it? What is dry ice, first of all? Is it water?
Yeah.
It's not water.
No.
What is it? Dry ice. It's not water at all. It's actually frozen CO2. So it's CO2 in the solid phase.
Carbon dioxide.
Carbon dioxide. Now, when you leave dry ice out on the counter, what do you see coming off of it? CO2 in the gas phase. So it's just CO2 vapor. Shipping companies like UPS, FedEx, they love dry ice. How come? It keeps things cold, and it doesn't get things wet. And if you're using cardboard boxes to ship things, do you want it to get wet? No. So UPS and FedEx use a lot of dry ice because it keeps their substances cold, but it doesn't get wet. It just will vaporize. It sublimes and becomes into the gas phase without getting wet. And so it's kind of cool, this dry ice. You can put it in water, and the heat goes into it. Heat will go into it, and then the gas comes off, and it kind of looks like a cloud here, but it's kind of cool stuff to experiment with. Okay, but that's called sublimation, when you go from a solid directly to a gas. All right, there's one more. It's called deposition. Okay, this is when you go from a gas directly to a solid. Okay, if you're going from a gas, so let me draw it up here, the gas phase, directly to a solid, predict what's happening to the distance between the molecules. Yeah, the distance here has got to get a lot closer. So the distance gets smaller, and the intermolecular forces become stronger because they're so much closer together. What's happening to heat flow? Does heat got to go into it, or does heat got to leave? Heat has to leave. How come? Yeah, because these have got to slow down, don't they? These particles have got to slow down. They've got to lose heat. When they lose heat, they'll slow down so quickly that they get so close together that it makes a solid phase. So it's got to lose heat. Whoops, I'm going here. Heat is released from the gas into the surroundings. Okay, where do we see deposition? Yeah. Let's talk about this for a second. We've all experienced this. It's a cold winter night. Your car's parked in the driveway or in the street. You come out, there's no storm. It didn't snow, it didn't rain over the night. And you come out and there's frost on the windshield. Well, where did that frost come from? The air. Okay, so there's...
Would have gone to water and then to a solid?
You would think, but sometimes it's cold enough that it will take it right from the gas phase. So this water that's in the air, called humidity, that's how we measure it, will hit this cold windshield. And if it's cold enough, what's called deposition, it just deposits itself on the windshield in a solid phase, known as frost, right? And so it happens instantly, and that's one example of deposition. So. Yeah, and you can see a lot of cool crystal structures here and how it forms, but it's coming from the air. Even though it didn't rain, it didn't snow, that's where frost comes from. Okay. I have a diagram here. It's called a phase change diagram I'd like to talk about. There's more to it than just temperature. Okay? Temperature has a big part, but what phase you're in also can be determined by pressure. So what you'll notice here, the vapor phase or the gas phase is this blue color. The solid phase is this green color, and the liquid phase is this brown color. But it all kind of has an effect on temperature and pressure. All of that goes into determining which phase you're in. And every substance has different boiling points, different freezing points. And so this is the phase diagram for just water. So it can get kind of complicated if you're moving to other substances. But I wanted to end with this one. So I would like you to all look up here for a second. Whenever you have a graph, what I would do first, guys, is look at what the axes are reporting. This y-axis is reporting what? Temperature. The x-axis is reporting what? Heat absorbed. So as you move to the right, you're absorbing more heat, right? So it's got, and then now let's look at what it's reporting. Solid, liquid, gas. Boiling, melting. So what I would want to do, let's talk about the solid phase here. Let's talk about water. There's an ice cube. The liquid phase, there's a puddle of water. And here's the gas phase. So I've got a few questions to kind of review what we just learned. First of all, what do we call it when we go from solid to liquid? What phase change is that? Melting. Melting. Does this, for melting to occur, does this ice cube have to absorb heat or release heat? If this ice cube is going to melt, doesn't it have to absorb heat? Yes. It does. And so it's got to absorb heat. Remember, as you move to the right, we're absorbing heat. Okay, good. Let's go from the liquid phase to the gas phase now. What's it called? If we go from liquid to gas. Vaporization. Okay, good. Does heat got to come into this liquid water, or does it got to leave? It's coming in. We're absorbing heat. It makes the molecules move faster, gets them farther apart, and you form the gas phase. Okay, now let's go in the reverse order. What do we call it when we go from gas to a liquid?
Condensation.
Condensation. Good. Does heat got to come into this gas, or does it got to leave the gas phase? It's got to leave, because now if heat absorbed is to the right, heat released would be to the left. So it's got to release the heat, makes the molecules move slower, gets them closer together into the liquid phase. Good. What do we call it when we go from liquid to a gas, or liquid to a solid? Sorry. Freezing. Does heat got to come into this liquid water, or is it going to be released? It's being released. Okay, you got to lose that heat. It slows down these water molecules so much that they get close enough that they can be a solid. Okay. So very good. That's how many phase changes are there? 6 of them. Do we have a better idea of them now? What's happening to the space between the molecules and the intermolecular forces, and what's happening with heat? I hope so. Hey, before we finish, I wanted to give you some more practice on this. So in your student workbook, there is a worksheet, and it's titled Intermolecular Forces and Phases Worksheet. So please go to your student workbook now. Again, it's called Intermolecular Forces and Phases Worksheet, and hopefully this video helped.